Here to pitch Lux Semiconductors is Shane McMahon.
Hi, everyone. My name is Shane McMahon, co-founder and CEO of Lux Semiconductors. We are a microelectronics startup developing a new class of system-on-foil electronics. The rapidly emerging field of the Internet of Things, or IoT, will have major implications on a number of multi-billion-dollar markets, including aerospace and defense, health and wearables, and automotive and infrastructure. Enabling widespread IoT in these applications will require sensors, processors, communication, and power to be integrated together into a miniaturized conformal package. Unfortunately, this is not the case today. There is no clearer example of this than the instrumentation used in aircraft during test flights. Measuring simple variables like temperature and strain requires the use of large, bulky equipment with cumbersome wiring. Installing this equipment often takes months, since the entire aircraft needs to be completely opened up. And the size and complexity of the equipment greatly limit where these sensors can be positioned within the aircraft. In this application, users would love to transition to a lower profile solution that can be much more easily integrated into the aircraft structure. But existing sensors and their associated electronics simply do not meet the durability and reliability requirements. And a similar problem can be found in the automotive industry. Let's take a look at why this is. The most promising solution, flexible hybrid electronics, takes an interesting approach. They use low-cost printed electronics to print components like sensors and antennas. But since high-performance silicon processing and communications chips can't be printed, off-the-shelf packaged chips must be surface-mounted and soldered into place. When these devices are exposed to operational conditions, even mild stresses are enough to cause severe cracking at the joints, which can lead to single-point device failure. Despite the tremendous opportunity for flexible hybrid electronics, this singular problem has been enough to plague the entire industry for years and has significantly limited their commercial adoption. At Lux Semiconductors, we've developed an entirely new approach to overcome this major problem. The core enabling technology is a new way to make the most advanced semiconductor on the planet, silicon. For the first time, thin film flexible silicon is being used as a substrate to directly pattern many of the components that are typically soldered, including high-speed silicon circuits. The benefit is a complete circumvention of conventional failure modes, including the plaguing problem, joint cracking. To complete the device, the same durable print processes used in flexible hybrid electronics are applied to print components like sensors and antennas. The result is that all the functionality necessary for an IoT device can finally be integrated into a miniaturized conformal package. We call this system on foil. Importantly, system on foil has been designed for scalable manufacturing. The process used to create the underlying silicon is capable of sheet-to-sheet or roll-to-roll production, a necessary precondition for enabling low-cost, high-volume devices. And the platform has been designed to be compatible with existing chip fabrication processes. This allows us to leverage tools from the existing billion-dollar fab infrastructure that's currently used in the semiconductor industry. Ultimately, we expect this new approach to lead to a new era of electronics, one where devices are seamlessly embedded into everything, from defense, automotive, and eventually consumer electronics. When compared to other flexible electronics platforms, particularly in key metrics like size, weight, reliability, and cost, Lux's system on foil comes out ahead. For example, although rigid PCBs can be combined with flex cables, referred to as rigid flex in the industry, the end result is poor size and weight, along with reliability issues at the connection points. Flexible PCBs and flexible hybrids have overcome some of the flexibility problem, but are both still plagued by high cost, large size, and low temperature ranges. The system on foil advantages have been designed in from the very beginning. We started developing this technology while pursuing our PhDs in nanoscale engineering at the SUNY Polytechnic Institute. Since then, we've received over $2 million in funding to accelerate our development from sources including the National Science Foundation, the Department of Energy, and the Department of Defense. We've also formed a deep partnership with Oak Ridge National Laboratory. We're members of the leading flexible electronics consortium, NextFlex, and we're also working on several cooperative research agreements with strategic defense agencies focused on advancing microelectronics. On the commercialization traction front, we've received support from 5 of the top aerospace and defense primes, and we're now planning to partner with 2 of them on joint proposals, specifically to embed our electronics into their systems. We've also received a purchase order from a major aerospace OEM and an MOU from an Air Force customer. It is this traction that has defined our beachhead market. Due to lower volume orders and the premium placed on reliability, we'll be first targeting use cases in aerospace and defense, specifically peel and stick temperature and strain sensors for monitoring of aircraft, conformal electronics for RF antennas for UAV and satellite systems, and pulse ox wearables for human health monitoring. As the technology scales, our roadmap to high volume manufacturing will open the door to massive commercial markets as well, including mobile,